universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Well, hello and welcome to Sky Tour Radio. I'm here with Tara down there, and we got Daryl over there and Amanda right there. How are you guys doing?
I'm great. How are you?
Fine, thank you. Fine, thank you. And Daryl, how are you over there?
I'm nominal, thank you.
Nominal.
Warp engines are online.
Warp engines are online. Tara, what's happening? How are you?
Oh, I'm great. It's wonderful to be here. Glad to be here.
You just had the MUFON meeting yesterday, I believe, right? The Mutual UFO Network meeting, yeah?
Mm-hmm.
How was
That's
that?
right. Oh, it's great. Interesting stuff.
Very good. It was David Marler, I believe.
Correct. Yeah, he talked specifically about his book that's out in his Triangle UFOs.
Mm-hmm.
It was very interesting.
Very good book and a very good researcher. Probably the quintessential UFO researcher on the planet right now.
Yeah, what a nice guy. Really cool guy.
Yeah,
Love
he
him.
and Kendra, they're wonderful people.
Absolutely.
Yeah. So David and I, of course, are good friends. Are very good to know him. He has a really great history. So I'm glad that he did a great showing at the Phoenix MUFON yesterday. That was great.
We're fortunate to have him, and thanks to everybody that came out to that. So that was great.
Yeah, fantastic.
And if you out there have a personal interest in MUFON, check them out every Tuesday night here on KGRA at 8 p.m. Eastern.
MUFON,
What's up? That's right.
What's up? That's right. I did one of those.
David Marler was a guest of ours, one of our early shows. Yeah.
Mm-hmm. That's right, because Amanda, you're producing that show, aren't you?
I am.
You are. That's right.
But I'm not part of the show. It's not a shameless plug. I'm plugging other people.
No, but that's okay. It's shameless.
You're still
for the
part
show.
of it. Yeah, that's
Katie Page is what branch does she run? She's head.
She's in Denver. She's in Colorado.
She's the director of
the director. I was looking for the title, director. And Katie Cook is going for her fielding and investigation license or whatever it's called officially. And of course, Chris DiPerno, who's is he a director as well? He's up there as well in MUFON.
He's in New York.
He's in New York. Yeah. I don't know if he's
Chris is a good guy.
Chief director, or I don't know the terms of MUFON. I know it's not a great plug, sorry, but if you want to know more, check it out Tuesday.
There you go.
MUFON.com. There you go.
And you go to MUFON.com as well. That's right.
That's right.
Well, look, I want to welcome everybody to Sky Tour Radio tonight. We're going to have a good time tonight, and Sky Tour Radio is kind of an offshoot of Sky Tour Live Stream, which is our live deep sky observatory. That on clear nights, maybe even tonight, if it's clear after the show, in Arizona, we will stream. We do live streams. We show people the night sky and galaxies, clusters, amazing nebulae, and all kinds of features of the universe. And we show them in seconds, not the many minutes or even hours that it might take to acquire a good photo. We do it in just a few seconds because we've taken the time to get a telescope that runs very fast and has a very fast optical system. And we have a large telescope. It's a 10-inch diameter telescope, so it's moderate. It's not giant. It's not tiny. And we get some really good results with that thing. And so we run it remotely, so it's out in the middle of the desert all by its lonesome. All right. Sometimes we need to visit it, as Tara can tell you, because she had to go out the other day and work on it, and she did a fantastic job.
Yay, Tara.
Yeah, that's right. Yay.
Thanks.
Yay, Tara.
Thanks. Yay, Mark. Yay, everybody. It's working. Yay.
If I was your boss, I'd give you a raise.
If we had a way to pay salary, she already would have had one. So
it's all fun.
The telescope is very reliable generally. So we actually have a really good setup out there. It's in a building with a roof that rolls off, and it's just beautiful. And I run it from here in Connecticut, so it's 2,500 miles away. So you can imagine if something does go wrong, in those rare moments, you can imagine what it must feel like to be 2,500 miles away and not being able to go out to it and see it. And that's where this one comes in here. She just gets up and says, I'll go, runs out to the desert, and ends up getting on the property, going to the building. And then we talked on the phone, and together we troubleshooted what was wrong, and we managed to get it working again. And again, it was a small problem, but it's a big problem when you can't sit in front of the computer and see it. And this time we needed to have somebody in front of that system. So I wasn't sure how long it was going to take. And for it to be one day, in fact, for it to be like 2 hours, wow.
Yeah, it didn't take that long. Thank goodness.
No.
It was nice and cool.
She's very efficient, Amanda, but don't tell her. It'll go to her head, you know.
Oh, she's you owe her a lot to keep things
yes, we do.
there.
Yeah, we do. Yeah.
Nothing.
So our wonderful, gorgeous images that we take are made available to everybody. They're on an active server that is the pictures are up there minutes after we take them, not even sometimes seconds after we take them. The pictures appear on our cloud server, and the address is a free spot, place to go. You can go there right now if you wanted to, but don't, because we're on the air. But you can go there at any time and see pictures going back months and see all the latest and greatest going up to just days ago, not a couple days ago, from when we last streamed. So the pictures are all up there for you to use. They're free, no charge, and no gimmicks. So we don't want anything.
What is the site?
Well, it's actually a server site that has a link that I'd have to give. But if you want to,
so you can't look for it yourself.
Yes, you can. Because in every one of our streams, on SkyTour live stream, which is on YouTube, channel on YouTube, and every one of our streams in the description, you go right down and it'll show you the actual link to this particular server. You can go out there, click on it, and boom, you're in the server, and you can now wade through all these directories and see all these beautiful photographs. But it is SkyTour live stream on YouTube, so check it out and subscribe to it. Why not? It's all free. It's free stuff, man. And if you're not careful, you might actually learn something. And one of our
threaten the mark.
I am threatening him. That's kind of a thing. Oh, I get it. But then now he's being quiet. But down there, okay, Daryl hiding in the corner. He's not getting away. Okay, he's the co-host with me on SkyTour live stream, and he has some admirers of his own, don't you, Daryl?
I do.
Yes, you do.
Oh, you say so.
Mm-hmm.
I just posted a link to the server for.
Oh, you did?
Reference.
Perfect. Oh, fantastic! Thank you.
It's in our chat. I'll post it in general chat too.
Okay, yeah, fantastic. Yeah, so see, we make everything. We do it all for you. And why do we do this? Well, I'm an astronomer, and this is what we look like. So the bottom line is that I've always had this desire to let other people know what astronomy is all about. The study of space and time, actually, as it turns out. And that's what we do. We study space and the objects out in space, and we try to figure out how they work. And why would we do that? Well, because that science has actually catapulted our technology into the stratosphere over the last 60 years, and it's only getting better. We have the James Webb Space Telescope about 1 million miles from us, way out past the moon at a Lagrange point. That's a parking spot in space where with just a little bit of effort, it can stay there and stay parked there in this little elliptical orbit that it's doing out there for 10 plus years until it needs to be refueled, and maybe longer if we can figure out a way to refuel it, which they're already trying to do. But we have the opportunity with that particular telescope to look back in time to see galaxies that we cannot see right now because all their data is shifted well into the infrared because they're moving away so fast. And that's a property of a spectrum of something, is that it will get shifted into the red end of the spectrum if it's moving away from us. And there are galaxies out there so fast, moving so fast away from us and so far away that all of their data is out in the far infrared. And to be able to see it, we need a special telescope that can see the far infrared. And that's what the James Webb is. That's its primary mission.
It's going to pick up kind of where the Hubble left off. The farthest things Hubble can see are just dim little red dots way far away. And Webb is going to let us look at those little red dots and see them in all their glory at infrared.
Yeah. And it's going to go out almost to several thousand nanometer infrared size, which nanometers are billionth of a meter. And so light is small no matter what. But the longer wavelengths of that are what we call the red end of the spectrum and the infrared. And so James Webb is going to see what Hubble cannot, as Daryl said. And it's going to basically, it can see what Hubble can see like this, and then it can see way, way out here in addition that Hubble could never see. So that little narrow range of Hubble has now been supplemented by this rest of this. And you say, well, is that all it's going to do? No. It's actually also going to be looking at exoplanets. And because of the fact that when it looks at an exoplanet, it's going to be able to detect some of the infrared signatures that we can't see now with any of our telescopes. And these infrared signatures could tell us a lot more about the atmospheres of these planets themselves. Really, really hugely important. And the biggest thing there, the reason that James Webb can do it and Hubble can't, even if it was, see, the Hubble and the James Webb have a little bit of overlapping infrared coverage, just a tiny bit around the 5 nanometer range. Well, the best part is the James Webb Space Telescope is 21 feet in diameter, and Hubble is only 8. And the bigger the mirror, the more light you can see, and the better resolution you get for tiny, tiny little things. That's part of the reason why James Webb is so exciting to all of us astronomers out there. Yeah. So you're going to see a lot coming from James Webb, And, if you're interested, like I said, in seeing some wonderful objects at night, then tune in to our broadcast, SkyTour live stream. Subscribe so you get the alerts, okay? Because you want to be able to get the alert saying that we're going to be going live, all right? And make sure you select all alerts, okay? Like I wish I got an alert that my dog has bad gas because it really smells right now. She's sitting down here and it's just not nice, okay? Oh, sorry. It's an eye-watering episode right now. Jeez.
I used to know a German Shepherd named Barney that did that. We'd be playing Scrabble after dinner, and Barney would lay under the table, and boy, you knew when Barney was there.
Yeah, I know when Dingo's here.
Everybody would go, Barney!
Yeah. Well, anyway, where was I? Oh, yes, I was over here. So we're all set as far as the observatory goes. It looks like we're back in business. We'll be good there. And that telescope that you see behind me right there, that's the East Coast version. And we're actually on the cusp of making the building to put that thing back in. So we're going to get that done too. So we'll have an East Coast and a West Coast presence. So and we might actually have some options for East Coast where we might be putting it, a darker sky even than here. So that's a very, very exciting prospect. So you might say, are we doing anything tonight on this show? Or we're just going to talk about telescopes and SkyTour live stream. Trust me, I could talk about live stream all the time. Okay. Daryl knows he's on the live stream with me much of the time, right? We were on the other night, and I think we started at 11 p.m. Eastern, because that's when it got fully dark enough out in Arizona to start streaming. And we went to like 1:30 in the morning. So it was good,
Until things went south.
Well, yeah,
well, that wasn't the bad south, though. That was just...
no, that was just a simple issue.
You going to stream tonight, you think?
I hope so. Right after this show, I think we should be able to do it.
Right after?
Well, not quite right after. I have to wait till 9 p.m. Eastern in order for the power to the building to come on. Yeah. I have a timer out there. So the power to the building comes on at 9 p.m. Eastern, which is 6 p.m. their time. And it's not even dark then, but it lets me get in. It lets me open the roof. It lets me get the telescope temperature brought down to or up to the outside temperature. Yeah. It has to be ambient. It has to be the same temperature as the outside for it to perform as well as it should.
101 degrees there last I looked.
Hot and hot.
Yeah. Well, Tara knows. She was fixing the telescope at 111 out there.
Yeah, the time before this last time. Yeah.
39 degrees here.
Okay,
Wow.
stop. Jeez.
Wow.
Always got one of those in the crowd, don't you? 39 here. It's like, well, actually, that's too cold for me too. Anyway, that's too cold for me. 111 is too hot for me, and so don't feel bad about the cold, Daryl. Actually, sometimes really desired, especially if you're stuck in 111 degrees for a period of time.
Oh, well.
Yeah.
Deep subject.
Oh, here we go. Don't get her started, Daryl. You know, what's this
I had to put my winter clothes back on.
No kidding. Wow,
Yeah.
that's terrible. Wow. All right. Well, hopefully we don't need to worry about that here anymore. Although I mentioned earlier, I think before maybe I was on the air, we have a tornado watch right now. So if things go haywire for some reason, we might lose power. Then I nominate Daryl to take over the show and just finish for me. You got that, Daryl?
Sure. Why not?
He's like, what? Okay. Yeah. Well, in any case, a lot of you heard the news in the last couple of weeks here. And it has to do with black holes. Now, we've long thought in astronomy that supermassive black holes were in the core of many galaxies. We thought maybe those were sort of like the seed object in the center of a galaxy, because there was something more than this accretion of material and gravitational forces acting on singular stars at play in these galaxies. So we didn't know what was going on. So the theory was floated that maybe black holes, or more appropriately, supermassive black holes, SMBHs, love our acronyms, are in fact found in the center of many galaxies. And maybe that's the way things are. So SMBHs, the supermassive black holes, would basically be the nucleus which attracted other stars, which would form an accretion disk around the black hole, but very supermassively, and thus maybe a galaxy could be born from that. And large populations of stars would form in the chaos ensuing from this bringing together of massive amounts of gas and dust that is being compressed and ripped asunder constantly. But then you look at some of these galaxies and you'll notice that they have these beautiful spiral structures, right? So if we look, like, for instance, at Messier 33, this is in Triangulum, the Triangulum galaxy. You'll see that it has sort of a loose spiral structure, but you still see spiral arms, right?
I like that.
Isn't that pretty?
That's gorgeous.
Beautiful.
Love that one.
Yeah, this is beautiful. You can see a lot of detail in there, a lot of star-forming regions, which are the red things,
The color contrast in the spirals. I love it.
Mm-hmm.
Yeah.
Nature has the best palette of any artist.
Doesn't it?
Yeah.
And this is what's called a face-on galaxy. We're basically looking down on top of it, flat at us like this, So, but then we have galaxies like this, where we're almost looking at it edge on. This is known as NGC 4565, a very romantic name, but
also known as the Needle Galaxy.
The Needle Galaxy.
Right? I was going to say, I remembered one called the Needle, and I was wondering if that was it. It does. That's an accurate name.
You're exactly right.
Yeah.
I remember that when we showed this the other night, a couple of our viewers, Daisy and Zoe Amethyst, in fact, said,
"Oh, they're here."
Yeah, are they here? Oh, hi, Daisy and Zoe. They said it looks like a needle. So they got it.
It's like one of the gazillion space objects I can actually visualize. Oh, needle. Yeah. Okay, I get it. I see why they named it that.
Yeah.
As opposed to everything else that I can't see.
Well, most of us can't see them. Yeah.
Yeah, but you'll notice what makes this thing unique, not somewhat unique, is this large dark lane we call. These are dark lanes, and these are what these dark globs of dust that you saw here. You see this black dust, this dust in the galaxy, right off the center of the nucleus. You can see in the spiral arms, they're delineated by the blue stars and the dark dust. Well, from the edge, that stuff kind of looks like this. Now, obviously, this is not the same galaxy, but this is another galaxy that has spiral arms, but we're seeing it almost on edge. We're seeing it a little bit from below. And in the center of this galaxy may very well be a supermassive black hole. And then every galaxy has a different look to us at times. I mean, this one has a special name. It's called the Black Eye Galaxy. And this galaxy we imaged a couple weeks back, actually. And every time I look at galaxies, no matter where they are, I can't help but think that there's a civilization looking back at us. There's got to be someone looking at our Milky Way from there. That's my theory, right?
That's cool.
But I think it's a good thing to think about, because it'll keep you sane when it comes to how many possibilities there are out there. And then for our closest galaxy to us, we have this beauty. This is, of course, the Andromeda Galaxy. And you can see the dark dust lanes in that one as well. If this was on edge, it might look more like this guy, but bigger in our sky, you know. And so in the center of this galaxy, there might be, as before, a gigantic supermassive black hole. Now, these spiral arms you see in these galaxies, I mean, there's some new theories about how and why the spiral arms form within the galaxies. And I mentioned before, and a number of times actually, that when a galaxy rotates, it seems like the galaxy is rotating almost like a rigid disk. And when I say almost, that's kind of important. The almost is the important caveat. It's not quite a rigid disk. So there is a differential rotation, a rotation where the outer stars are slightly slower than the inner stars, but not nearly what they should be if we're looking at orbital physics the way it should be applied. It looks like the outer stars are going slower, but not slow enough for that to be the case. So we get these long, drawn-out strands of stars that end up getting, I guess you might want to say, I don't want to say wound up, but they get drawn out into these extended spiral arms that sweep back, right? And that's kind of one theory as to how the spiral arms might form, because we get a burst of star formation, and then differential rotation does the rest of the work and stretches the arms out in a spiral pattern as the stars and the galaxy orbits and rotates. Another details how a density wave theory could play a big role in creating spiral arms. The Whirlpool Galaxy, in fact, is thought to not have had spiral arms at all until the interaction with another galaxy that you see in all the photos of it. And that interaction may have caused a density wave, or let's put it this way, a wave of energy that went through that galaxy like a ripple. And that could have started the separation process and started this differential rotation and caused this density of spiral arms that we see in this particular galaxy. Now, how that all works is really pretty elaborate, but the easiest way to imagine what a density wave is by thinking of a helicopter looking down at a rush hour traffic. All the cars are moving in a relatively regular pace until they all start to slow down because they get to a traffic jam, right? There's a traffic jam where there's a bunch of exits maybe, and so those cars all slow down. So let's say they're all silver cars, and one of them's a red car. The red car, you'll see, slows down, gets into the traffic jam, slowly moves through the traffic jam, and then speeds up again when it gets out of the traffic jam eventually. All right? That's how stars orbit galaxies. They get caught up in this traffic jam of other stars, gas and dust in the galaxy, and eventually work their way free and continue on their way. So it's not the same stars in a spiral arm all the time. How's that for confusing you? But the spiral arms, though, are these concentrations that were induced by a passing galaxy or whatever, and then differential rotation, where the outer parts are a little bit slower than the inner, start to drag these out into spiral structures. We see this all over the universe, you know, and the oddest ones are the ones that have no spiral arms at all. They're just big spheres or elongated spheres of stars with almost no gas. It's just those are called ellipticals. Very strange.
Like M87.
Yeah, and that's actually one of the targets we're going to talk about tonight. You know, So either way, the spiral shape is a natural result of that differential rotation, okay? And even though galaxies spin like these semi-rigid disks, as we mentioned, there's enough of that difference in their orbital rates that those spirals can be drawn out in these beautiful spiral arcs. And we've noticed, as Daryl has pointed out on numerous streams, some of these spiral arms have real interesting crooks in their arms, as if they had some type of interaction that bent the arm. Right?
Broken.
That's right. Broken arms.
Mm-hmm. Poor galaxies.
Yeah.
And we got a lovely little thank you message for Tara.
Aw, thank you, Vera. That's
Vera,
awesome.
thanks you for saving your stream. And we were just talking about that earlier. Tara is Wonder Woman. Exactly. You called it, Vera.
Yeah.
You guys are too kind.
I think Vera got it right. Yeah, absolutely. So now, when we talk about, actually, I'm going to go on to something next, unless you had something you wanted to add, Daryl.
Can you put up NDC 4565 again for a second?
Sure.
Just rolls off the tongue, doesn't it?
Yeah, there it is.
The needle. Mark, are you in Photoshop? Could you possibly rotate that clockwise 90 degrees?
This is just an image. It's I don't have Photoshop running.
All right. Well, folks, I want you to put your imagination hats on and look at that image for a moment. If you see the nucleus of the galaxy there, the brightest part in the middle, and we turn that galaxy 90 degrees clockwise, so that left lower arm is now the left upper arm. If you projected that up on the ceiling, that is very much what we would see when we look up in the sky at night and see our Milky Way. Our southern horizon is pretty much just to the right of the nucleus of the galaxy, and what's to the upper right below that, above that, but below it to our point of view, that's down in the southern sky. And what we see in the northern sky is that nucleus of the galaxy above the southern horizon, and then that arm going to the left and that dark lane. We see very much the same thing in our sky.
Well, can I just mention that I was prepared for you to say that without knowing you were going to, because if you didn't say something similar, I was going to, because the next photo I have is this one.
Okay.
And there you go. This is a photo taken, believe it or not, at the observatory site just after sunset. You can see the orange of the sunset still there on the right side. And we have the full Milky Way visible to us like this. This is at sunset, guys. That's how dark it is.
Is the horse in that?
It is. The dark horse is.
Yes.
The dark horse is just below.
Yeah, the dark horse is there.
Right.
If you look close, can we zoom in on that possibly?
No, we can't. This is just an overlay. I can't.
Okay. There's a cloud there, a dark cloud shaped like a pipe, like you smoke a pipe, you know? That's called the Pipe Nebula. And that is the horse's back leg. His head is to the upper left of that, and his front leg's a little dimmer. Maybe you'll see the shape of a horse there. And actually, when you look at the bowl of the pipe, the brightest part of the Milky Way you see just to the left of that. That's the center of the galaxy right there. That's where Sagittarius A star is.
Right. Sagittarius A star is what they call the black hole at the center of our galaxy.
Wow.
So now, speaking, thanks, Genghis and Marco. Speaking of the black hole at the center of our galaxy, we, as I said, we always thought they were there. We always had an idea that they were there, and there's reason why we didn't just imagine these things, okay? Because when we looked at experimental data, I'd like to show you what we saw. All right. So what I'm going to do is I'm going to bring up this guy right here and get rid of this guy right here. Okay. This is this particular study started in 1992. 92. Okay. Some of you listening to this were probably born back then. And this study started in 92. These are all stars that you're seeing, and that plus sign indicates the center of our galaxy. Watch as they look at where the stars change over time and how their orbits change. You can see that the stars are orbiting something in the middle of this galaxy, right in the middle of our galaxy. Let's zoom in there. Now watch. We're going to watch stars come around and orbit something invisible. And then this one, whips right around. So that's the orbit it has. Now, this star, when it gets close to this part here, this is the location where it's closest to the black hole in the middle of our galaxy, or I should say the invisible thing that it's orbiting, is about 120 astronomical units from that. And if you notice, if we actually kind of back this up a little bit, all right, from about here, this was 2001 to about here, 2002. It was about a year to a year and a half that it actually took it to go by the black hole at the middle of our galaxy. Okay, just about a year and a half. So that what we're seeing right there is an unbelievable image, a video that shows what happens at the center of our galaxy. These stars are orbiting something there, and we figured it's got to be a black hole. It's a very, very massive object with a lot of gravity, but it's not something that we can actually visualize, because the black hole is, well, black. We see radio waves, we see gamma rays, we see other energy coming from it, but it's nothing in the visible spectrum.
And that 120 astronomical units, that's 120 times the distance from the Earth to the Sun. So that really, in the big scheme of things, that's not very far at all.
Yeah, well, if you're going by a massive black hole, that's true. This black hole is pretty large. But, you say, well, how large is it? Well, I can tell you, okay? So let's do that. Let's come out of here and let me bring this down and talk about that. This black hole that we saw is this black hole. This is the supermassive black hole at the center of our galaxy. It's called a variety of names. It's called SAG-A, Sagittarius A star. It's not a star. And so when they say A star, they mean the asterisk after the designation. But it's confusing for people to hear it because they think it's a star. It's not a star. It's a black hole. So, but that's all there is to that. And every single black hole we look at looks like a kind of a weird donut, and that weird donut shape is for a very, very important reason, which I'll tell you in a minute. But just by way of comparison, and Daryl, jump in here because I know you have a few things to say. Let's take a look at both of these. Okay, this is Sagittarius A on the right, and this is in our galaxy, 27,600 light years from us. And this is Messier 87, 55 million light years away, but a much larger black hole. And for a size comparison, this is the size comparison, right? You'll notice that the orbit of Mercury on the right, that's the size of Sagittarius A. Overall that we're seeing there is that it's within the orbit of Mercury. It's not that big. But on the left, you can see Messier 87 in Virgo, and you can see that Pluto's orbit is that small circle labeled Pluto's orbit, and the black hole is several times the size of our solar system. That's huge. That's huge.
I had a question for the video. I think our audience really enjoyed that video. I know I did. In the top right corner, it said 10 light days. What is that in reference to? Is that how far away they were looking, or?
That's just the scale of distance at the center of the galaxy.
Yeah, where were you talking from when we're looking at?
When you had the video on the left, it was counting from 92 to whatever. See, it says 10 light days. What is that in reference to?
That's actually a distance. That's the distance light travels in 10 days visually on the screen. It's showing you that.
Yeah, you could say that's about 1/36th of a light year.
Yeah. So if we're looking
trying to wrap my head around that still. Yeah. I'm sure our audience gets this, but
well, okay, I'll give you an idea. Okay. How far is the sun? It's 93 million miles, right? It's the astronomical unit. But it's 8 light minutes away.
Yeah.
because it's that close. But if you can imagine, you could go to a certain point where you'll be 10 light days.
Okay, that's what I was wondering. So, but is that counting from Earth or from the black hole?
That's counting. That's counting this image. It's showing you on this image how far light travels in 10 days on this image.
From Earth.
At the distance of the Sagittarius A star.
Right.
At the distance of the center of the galaxy.
Just the images themselves, the movement of the images to start over is 10 light days.
That's at the distance of 27,000 light years.
Right. 27,600 light years. And at that distance, okay, this at this distance, this magnification, this particular video, as I said, in this image, this is how far light would travel in 10 days. And that's the scale. That's basically like a scale. The scale of this image that's 10 light days in size, basically. All right. And then as it zooms in, that gets bigger because we're zooming in on that location. So that scale gets much larger.
Like I get that we're zooming in, and I get that we're watching this for years and years.
Yes.
But I mean, I'm not going to take up too much time because I'm sure everyone gets this. I'll save this for later on. But
okay, let's put it
like
this way.
How is this just like a computer program, like our best estimate? Because we don't have something at the center, like at the center of the black hole, to be measuring 10 light days away to be filming this. You know what I mean? Like, I'm not.
I understand where you're going, but let me explain. When you're looking at the black hole and you're looking at this star, okay?
From where?
From here, this image, this particular zoomed level. Okay, this star, okay, and say this star, let's for argument's sake say that they're the same distance away from us. But how far are they from each other? Well, if this star's light is, say, let's say it's 5 astronomical units away, it would take 5 times 8 minutes for its light to reach this star. So this would be a 40-minute light travel time. But if you could make this star farther away, then you could see how you could be 1 light day away from this star, for instance. Mm-hmm. And so basically measuring how fast it would take light, no matter where it's being emitted from, to go on an image, for this to be a scale of 10 light days means that this is how far it takes light to go in 10 days. 10 days meaning if this star emitted light, it'd be over here 10 days later.
If you could imagine, again, when that star was closest to Sagittarius A star down at the bottom of the ellipse.
I'll make that happen.
And you said that was 120 astronomical units.
That's right.
Well, an astronomical unit is 93 million miles times 120. So you're talking, I don't have my calculator in front of me, but
it's 120 times 8 minutes.
Yeah, 120 times 8 minutes.
Right.
And that distance is a fraction of what that 10 light days is up at the top.
Right. So it would take, it would basically be, it'd be a small number. It wouldn't be 10 light days, but it would actually be a much smaller number, because if you say, like, if it's 120 astronomical units and it takes 8 minutes per astronomical unit, 8 times 120, right? Is that 1160?
I'll take your word for it.
Okay, so it'd be about let's round it up, say 1,000 minutes light time. All right, and when it's far enough away,
960.
Okay, so when it's far enough away, it's going to be maybe 5 light days or 8 light days away at its farthest, because that's how long it would take light from the star to reach the black hole. So that's showing you basically the scale of this zoom. All right, we're able to see something down to just a few light days across, and that's pretty good. That's why this is such a monumental video, taken for like a dozen years to get this. Mm-hmm. So I think when you look at this, this points out to me the strangeness that are black holes. Now you'll say that, wait a minute, this star here, it just seems to be going by it. What's going on with that? How come it didn't get stuck with it? Well, probably because of the fact that this star might be either way closer to us or way further away. So it's not as close to the black hole. So it's just wandering by the field. It's not wandering by the black hole per se. All right.
Yeah, it's a line of sight thing.
It's a line of sight thing. Yep, that's right. So that's just a cool video. And when let's just watch this from this point of view. Now, some people have said, well, when this star comes through, you'll say, wow, it goes whipping around so fast. Any planets it had must have been whipped away and taken off. Well, let's suppose it did have planets, okay, for argument. It took 1.5 years for the star to go by the black hole. Yes, it accelerated. Yes, it went fast when it went by the black hole. But it still was maintaining its planets. If it had planets, they still would have been going around. They wouldn't have known any different. They wouldn't have suddenly felt, oh, we're accelerating. They wouldn't feel that because it would be very gradual. Then the entire system would be accelerating. So you wouldn't necessarily know that you were accelerating, just like you don't feel you're accelerating now, but you are. All right. So the point being that this may not have been a big destroyer. And the other thing too about our black hole is that it's really not growing anymore. They grow when they absorb material. Now, there might have been a point in the recent past where a passing dust cloud was absorbed by the black hole. And yes, it would grow a little bit from that. But our black hole is kind of being starved, in fact. And that's what astrophysics people have been saying. It's sort of starved of material. It hasn't had a whole lot going on.
Yeah.
So it's there. And the thing is, over time, if you keep starving a black hole, well, it's going to evaporate.
They made a point during the ESO news conference about Sagittarius star that if our black hole, Sagittarius star, was a person and you fed that person a grain of rice, you wouldn't feed them again for 1 million years. By comparison, I think is how they said it.
That's a good analogy.
When we look at M87 by comparison, though, M87 is huge. M87 is eating a ton of rice. Put it that way. It's really wolfing it down, but it's so big it moves slowly.
And that's M87 on the left that you can see in this image. And again, notice Pluto's orbit, that little circle. You can put Pluto's orbit multiple times across the center of this object. Now, you notice they both look like donuts. And you also notice that they look approximately the same size, left and right. Well, that's because the M87 is about 1,500 times more massive, 2,000 times further away than Sagittarius A. But Sagittarius A is also that much closer to us. So it looks bigger in the sky, and it just happens to be approximately the same size. But you look at the shape. Why do they look like donuts? That's the thing that's interesting. And that's the thing that I'm going to mention and mention to you right now, because I have a little toy that I made for you. I made a black hole to show you tonight.
Cool.
Okay. This is the accretion disk, the disk of material around the black hole, the thing that you saw in orange. I painted it orange just because it was the color they show. Here's my black hole. It's actually a copper ball. And if you know, these are rotating now. The black hole is rotating. The material is rotating around the black hole. But this accretion disk is like the disk of the solar system, like the disk of the galaxy. Disks are a common thing in the universe. They actually occur naturally. Accretion disks form. Toy time with Mark. Yes. Okay. Yes. Yay, toys. They occur naturally in the universe. And let me show you what happens. This is the black hole. It's actually extremely gravitationally strong, right? Obviously, it has a very, very high gravitational field. We know that gravitational fields bend space. What? What does that mean? Well, I will show you. Let's imagine that you have a car driving on a hill, Okay, the car follows the contour of the hill, goes up the hill, down the hill, up the hill, down the hill. Why is it doing that? Why is it just going straight? It's not going straight because the hill goes up and the car is constrained to follow the road. It's constrained to follow all the curves, go up and down. Okay. In the same way, light is constrained to follow the universal path laid out for it by the fabric of space. Light follows the curve of space. So, space-time, that's right. So, when you have a disk like this rotating around a black hole, and here's the far side is over here. You can't see it, but here it is. Okay. You can't see it, but the light's going in all directions. It's going out from the accretion disk. Energy of all kinds is going out toward you, going up, going down, everything. But the light that goes up from the accretion disk is being bent around because it's following the deep curves caused by the black hole sucking, the fabric of space into a very, very deep curve. And so what happens is the far side light from this far side looks like this to your eye. See that? It looks like this because of the fact that the light rays go up and then get bent toward you because they're curving right around the top of this very, very steeply bent space near the black hole. But you can see them because they're not getting to the event horizon. This is the point of no return. They're just above it. So you see this material. So this is why black holes look like this to you.
Yep.
You saw this in Interstellar, and Kip Thorne. I had the pleasure of sitting with Kip Thorne for hours talking about black holes, in fact. And this particular shape is something that is predicted by relativity. And we found this shape exactly as predicted when we looked at Messier 87. And now we're finding that shape exactly with Sagittarius A. And so I can say it's as expected.
Yep.
But that's it right
and
there.
If you put M87 and Sag A star both up again, this is why, and I think the ESO scientists were a little nervous about this during the press conference, that as long as they keep using the same techniques, every black hole we look at is going to look like every other black hole.
That's right.
In general. Now, Sag A star on the right there looks different in detail, but in general, you look at it and what you see is an orange donut.
Yeah, and you see those bright spots, and people say, well, how come Messier 87 on the left has sort of a ring around the bottom here, and Sagittarius A has these hot spots? Why the three hot spots? Does that mean they're different black holes? Well, certainly they're different actual black holes, but the processes that they're going through are the same. But the different, there you go. That's, I think, what Charles is asking. Why are there lobes? I'm going to talk about that. Okay, first, let's look at Messier 87. On the left, you see that bright ring? Okay, that's a Doppler shifted value. That's the part of the accretion disk, okay, that's doing this. I'm going to show you right here. I'm going to bring this up. Okay, that's the part of the disk. Thanks, Amanda. That's the part of the disk that's actually coming toward us as this is spinning. Remember I told you it's spinning? As it's spinning, all right, the material that's coming toward us is shifted a little bit into the higher end of the spectrum, a little toward the bluer end, not into the blue, but toward the bluer end. So it's higher energy. So it looks brighter on the radio spectrum that we look at. All right. So that's why we're seeing these lobes down here that are brighter. And when we see the curve, again, the curve is due to the fact that space is bent and the light that's going up is bent over the top because it's following the curve of space. All right. So going back, yeah.
Well, there is a question. I think it's a great question from Uberku. Would that red ring be spherical surrounding the black hole in reality?
It's an accretion disk. It's a plane.
Yeah,
as Mark just said, the light is being bent over and around the top of the black hole, so we see it like that.
Yeah. Now we have an additional problem, and this goes to Charles' question about the black hole. In fact, let's just look at Sagittarius A right now. The additional problem we have is that this particular telescope that captured this is called the Event Horizon Telescope. Now, the Event Horizon Telescope consists of a number of telescopes around the world. In fact, this is what it looks like. There's 8 telescopes, counting the South Polar Telescope. That's okay, Uber Crew. I'm glad you asked. All right. Counting the South Polar Telescope as well, and the telescope in Chile, the United States, Mexico, Hawaii, and Europe. And as the Earth rotates, they each get different observations with these big radio telescopes, and then they're coordinated, normalized, and aligned with each other to make one big 8,000 mile diameter telescope. 8,000 mile diameter is the diameter of the Earth. Now, to see this a little better, okay, let me show you how that looks. All right, this right here is the actual. This guy right here. This is the actual size of this. The Earth, as you can see, 8,000 miles across. But then we actually see this. Now we see this data. This lines connect one telescope to another. So watch now. All right, as we move the Earth, as the Earth rotates. Now these 2 telescopes on the left of the screen come into view and start capturing data. Meanwhile, the one in the upper right drops off in a moment. Okay, and now you're just left with these. Now, what happens is these are all taking data, and the data looks like this. This stuff on the right here in this circle. The red dots indicate data points. Taken together, this is 8,000 mile diameter measurements. Now, it's not a full-blown measurement. Obviously, it's crude, but it's good enough that we can actually see what's going on. Now, consider, and we'll watch this again, consider also that when we watch this, you're looking at 8 data points, 8 telescopes capturing data for a certain period of time. And that certain period of time is a few hours each. You got to understand, black holes are faint. They're not bright. So it's going to take a long time to actually capture this data. All right. So they're doing this. They're capturing this data. And as they do that, the data is being sent down to a central location where it then becomes coordinated and normalized for the curve of the Earth, the time at which and most importantly, the time at which the signals get to each telescope.
Yes.
Now, that's important because if we look here, this telescope here gets the data first. This telescope gets the data second. But here's the Earth. Now, if the data is coming from out here somewhere, okay, it hits this one first and it hits this one second. Okay. And it doesn't hit this one at all. It sees different data, as does this one, as does the Hawaiian telescope see different data. All right. So in that time, which is several hours, in that time, what happens is that we watch the data change. And when we look at Sagittarius A here, this image here is blurry. It's blurry because we have so much changing over the time it took to make these observations.
Yeah.
And so every hot spot is dragged out. Every detail is fuzzed out. So we can't get a really sharp and crystal clear image like the little toy that I showed you, like the little prop I showed you.
Yes. The ESO scientists made the point that this is what they called a smoothed image.
Yeah.
This is an average of a lot of different images. This is where the scales of the 2 different black holes come into effect. That Sag A star is so much smaller than M87's black hole that we see things move around Sagittarius A star in a matter of minutes or hours, while M87 is so much bigger, it takes us days or weeks to see much motion.
Yeah,
it's like it's so darn big.
Yeah, it just takes an hour for material to go around Sagittarius A roughly, and it takes like approximately 2 weeks for data to go around Messier 87.
Yeah, if the video was out there, you'd have to look for it. They showed this during the ESO news conference of like snapshots from instant to instant of what was going around Sag A star, and it's really fascinating to watch. It's very sharp and it's very streaky. One point to be made too, though, is that these are from radio telescopes. They are not photographs. They're not images as we come to expect them or understand them, with conventional instrumentation. They're radio images. back in the day, Mark, I'm sure, remembers radio telescope images were just colored blobs. They didn't really look like anything.
That's right. Yeah, they were actually colored with primary colors. You actually had red, green, blue imagery, orange, and yellow, and they kind of were graded. And I actually built a radio telescope, and it consisted of a truss work of wooden poles with fine wires strung between them. These fine wires were very sensitive to the resonance created by Jupiter's moon Io, the closest moon to Jupiter, and we could observe the torus of elements that surround Jupiter that are shed from Io as it goes around Jupiter. We could actually observe that torus using this technique, and we had with graphs. We didn't have it was like sodium, I think it was.
Yeah, sodium.
Yeah. And that's interesting too. And we'll get to we'll talk about Io someday, but here's something to keep in mind. Io has an extremely tenuous atmosphere. Just an aside here. So let me go over here because it's sort of an aside, okay? So an aside over here. Io's atmosphere is very tenuous. So what happens is on the night side, the atmosphere fully rains out and ends up on the ground as frost, okay? Frost of the sodium ions and sodium material that's the atmospheric components, including sulfur. And then when it comes around the day side, that stuff melts and goes back up to form a tenuous atmosphere. So by night, Io's atmosphere is gone, and by day, Io's atmosphere is back. Isn't that crazy?
That, you know what? I have a perfect analogy.
Yeah.
We'll go to break and disappear, but then we'll be back in about 3 minutes.
Very good, Amanda. I love that. Thank you for that absolutely brilliant segue.
It's what I do.
It's what you do.
Okay.
All right, folks. Well, as she says, we've got to listen to her. She's Comanda. See, it says right there, Comanda. You got to listen to Comanda. We'll be back right after these messages. Don't go away. There's a lot more.
Hey members, the new KGRA DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
Scrolling all day, time can disappear. Wanna make it count? Why not volunteer?
Posting pics of your food, that takes up time. Time, you've got time to binge all of season 9, though it got so bad.
Time, you got time. We're gonna grow back and be the same browse you had.
Just a few hours to keep families from harm. Help us end home fires with Sound the Alarm.
Volunteer for a day to install free smoke alarms in your community.
Discover the Observation Deck, a one-of-a-kind virtual event platform that takes video conferencing to the next level by using avatars to navigate a campus. There's so many areas and activities to choose from. There's a 1,000-seat auditorium, an expo hall, a nightclub, and even a beach. So come attend a conference, take a class, or hear a lecture on the incredible Observation Deck campus. Go to theobservationdk.com.
You're listening to the KGRA Digital Broadcasting Network. We provide unparalleled coverage of trending news in the world of ufology, cryptozoology, and paranormal phenomenon. Whether you're watching our video live stream or listening to one of our audio programs, you are getting the best from world-renowned researchers and hosts, guiding you through topics the mainstream won't touch. Miss one of your favorite programs? No problem. Head over to the members area at kgradb.com for access to our massive library of award-winning content. Make contact, stay connected, only at kgradb.com.
Anyway, so where were we? Oh, yes. We were talking about the black hole and the reasons why Sagittarius A and M87's black hole look sort of the same. And we talked about some of these other, some of the other information that the scientists had given that Daryl had mentioned to us earlier. And you now know about the shape and why it looks like this, because the light rays going up are bent by this steep gravitational field over the top of the black hole. And so everywhere you look at it from, it's going to look like this. Everywhere you look at it from. It's
every black hole is going to look like that.
Every black hole is going to look this way. They might be bigger, they might be smaller. And depending on how far away they are, it might be sharper or it might be more blurry. Mm-hmm. So
I have a question to that, if I could.
Yes, you may.
Please. Well, so there's an accretion disk on the black hole. So we're seeing it like you showed the galaxies kind of edge on, and then you see the disk kind of flipping up behind it. What if the galaxy is facing us at a different angle, like this? Do you see a solid donut type of thing, or how can they all look the same if they're oriented to us differently? I guess.
And they will look very different from a certain point of view. However, let me see if I can do this. Okay, from this position, you'll still get a donut. From this position, you'll still get a donut. From this position, you'll still get a donut because this material is going to go up. This is going to be Doppler shifted, and it's not like it's totally flat. There is some thickness to it, so it's going to go around the middle of that black hole. All right. And don't forget that if you're going to be like this, you're going to have some that's going down, some light rays that are going down the bottom are going to be shifted towards you, and some light rays from the top are going to be shifted towards you. So no matter what side you're looking from, you've got light being shifted towards you from that steep gravitational field everywhere on this object. So no matter where you look at it.
Per Tara's question, and I don't remember the details of how they figured this out, but we know, they said M87 and Sag A star have different orientations, that we're looking at different angles.
About 50 degrees for this one.
Yes.
For Sag A. Something like this. So about like that. Like that.
Uh-huh. And if I remember right, M87, I think we were seeing it closer to edge on. And, of course, we know the orientation of the plasma jets coming out of it, too, which are pretty good indicators of how it's tilted.
Yeah. Keep in mind that when he says plasma jets, when a black hole has an accretion disk, those plasma jets are going to be going up and down from the north and south poles of that black hole. And that particular orientation gives us big clues as to how things are shaped and arranged. So when we look at, for instance, this one here on the left of M87, wherever its jet is located, we know that the North Pole is in that rough direction. And then based on an analysis of the material and the Doppler shifting, the brighter stuff coming toward us, dimmer stuff going further away, we can kind of figure a little bit more about how the angle is set to us. But it doesn't help that we're observing things for an hour at a time or multiple hours. And we're getting, as Daryl mentioned earlier, this smoothed image of data. The one on the right is definitely blurrier than the one on the left. Okay. Yeah. If you look at the one on the left, that central black area is far more well-defined than the one on the right. All right. And so that is part of the problem we have here is we don't know exactly how fast that material is moving around the center of the black hole until we actually image it and get data from it.
Yeah, and the strength of the plasma jets too. M87, heck, we have seen one of the plasma jets coming out of M87. It's visible in Mark's telescope.
Yeah, we did with Skytra Livestream.
Yep, and M87 is so big and it's consuming so much matter that those plasma jets are very strong, very big.
Yes,
while the plasma jet out of Sag A star is, I forget the particulars, but there's not much of one there because as they said, Sagittarius Star is starving in comparison to M87.
Yeah, it doesn't
not
have
considered very much.
It doesn't really have. There's an interesting lobes that are visible.
Yes.
Very interesting lobes. I think they're Heisenberg lobes.
I forget, but I know what you're talking about.
Yeah, and there's like these large areas they seem ancient. So it might have been at a time when the black hole was more active that these occurred. But that kind of gives a clue where the north and south poles may have been at one point. But don't forget, a black hole, because it's rotating, it could also be precessing. It could be rotating like a top.
Uh-huh.
So that area could be doing this just like our North Pole does. There's no reason it can't be precessing. It may very well be. So we don't know for sure. And that's the beauty of astronomy. We got to figure this stuff out. Oh, yeah. That's just great.
It's so interesting.
Is it not?
It is.
Is it not?
Mm-hmm.
Now, I know that in the second hour here, we want to have Daryl do the deep dive. We're going to talk about the lunar eclipse that we had. If any of you have more questions about the black hole, feel free to ask, okay? Because we're here all night, guys. No, and if you if we do stream after, you're free to ask questions there as well at the Sky Tour live stream. And I want to thank everybody.
People are already viewing over at Sky Tour live stream on YouTube, and
excellent.
Of course, people here on KGRA DB. Thank you for your support wherever you're tuning in. There's some people on Facebook, so we appreciate you all.
Awesome.
Yeah, there's good people out there. You know that. A lot of people are hungry for knowledge. Really, really nerdy, hungry for knowledge. Thanks, Dee Dee. Well, thanks, Charles. That's very kind of you.
Kathy likes your black hole. She thinks it's cute.
That's a cute black hole. I know, but it's like a UFO too. Like
visuals help because this is so hard to wrap your head around. I mean, these are crazy concepts, so visuals always help me. Yeah.
This is the part that matters, right? When you consider that light's going in all directions from this accretion disk around the black hole, all directions, right? But the light going up is bent because it's following that steep curve from gravity that's created by bending of space near the black hole. And that's why this far side looks like you can see it. You really can't. It's here. It's not visible, but the light goes up and is bent towards you, so you do see what's on the far side. And it's always a distorted view.
Yeah, I hate to sound negative, but and I wondered this during the press conference that ESO did, European Southern Observatory.
Mm-hmm.
If those scientists weren't a little bit nervous because they looked so much alike, and I may have said earlier that as long as they're using the similar techniques, every black hole they look at is going to look sort of like the last one, It's another orange donut. Look at that. It's another orange donut.
I was elated, Daryl. I'll tell you why. Because
certainly, so was I.
Because obviously, and I think that they were probably not nervous. They might have been nervous that they were on TV, okay? Because there are people like that don't like being in front of a camera. And in fact, a lot of people in science don't like being in front of a camera.
Yeah.
Okay.
Well, one thing I know about scientists, they're always worried about their funding. And
That's
if you show us a dozen black holes that all look like each other, they may start worrying. But the good part of this, I think, is it's going to keep pushing technology. And whether it's adding more telescopes to the event horizon or new technologies or whatever, that's going to keep pushing the envelope. And hopefully we'll get to see more with the ones coming down the road.
Yeah. See, until we actually can move off world, get off the planet, we're still constrained with the 23-hour, 56-minute, day cycle. We're still constrained to the 365-day year cycle. We're always moving. We don't have a stationary place to sit and just watch what's going on. Even if we went to a Lagrange point, that's moving too. It's orbiting the sun, just like the Earth, just like the moon, just like everything else. So to actually be at a point where we're at absolute zero movement, no movement with regard to anything else, where we could actually set up a telescope and look, then we wouldn't be able to image something perfectly. We're always going to have a little bit of problematic imaging. And with Sag-A, this is moving very quickly. See how fast that's rotating? It's going around once an hour, basically. So all that material is being photographed in like an hour's time. So you're getting this drawn out smear.
Right. That's the smoothing.
That's, of course, yeah. And that's that smear is the result. And so it may look like this, but these hot spots, we can learn a lot from these hot spots, and we have. There's again, the stuff coming toward us is the material moving in the disk around the black hole, coming toward us slightly. That is shifting it to a higher part of the spectrum, because that's like a Doppler shift. You know about Doppler shift with sound. Something comes towards you, it's like, and it goes away, right? We're familiar with that. You hear it all the time. Whoa, what was that? Something's zipping by, a guy in a motorcycle. Well, that sound difference is just not real. It's not really happening on the motorcycle. If you're on the motorcycle, riding with the motorcycle, you're just hearing, you're not hearing it change pitch. Only someone watching it stationary hears the pitch change. And that is what we're seeing.
Yeah.
As this object is rotating, the stuff coming toward us is basically changing light pitch, if you will. It's changing to a higher frequency. Sound changes the pitch. Light changes the frequency when it's coming towards you or going away. When it's going towards you at high speed, that's a blue shift. Things get shifted in the blue direction. Not necessarily into the blue end, but toward the blue. They go farther back in the infrared just a bit, and then deeper into the infrared when they go the other way. And that's what we see. It's the forward and back motion. And that's a huge, that right there is a huge methodology by which we can look at planets around other stars and figure out a lot about them based on the movement of the star. It's one of the original things we did. We studied the spectra of the star and saw the lines in the star, the spectral lines, were shifting. What did that mean? It meant that the star was doing this, coming toward us and going away. Why? Because it's orbiting something. And it's minuscule gravity. If it was two stars orbiting, say a black hole orbiting and a star, okay, if this was a star, then you'd see a big shift as the star comes towards you, and then a big shift as it goes away. You wouldn't see the black hole, right? But that shift would tell us there's something there. We'd see that shift in the spectra of the star. A blue shifted line at one side, then it goes to red shifted on the other side. And that's kind of what we see with this accretion disk. We see blue shifted on one side, red shifted on the other.
Well, that might relate to what OG Skywatch has a question. He heard some of the stars circling Sagittarius star are moving at or near the speed of light. There you go. If I remember correctly, I think one or two of them, they said we're moving like about 25% of the speed of light.
Yeah, that's a little bit of a exaggeration, OG, if you heard that from someone. I'd love to think that stars can move near the speed of light, but so far we haven't really found any stars moving near the speed of light, in actuality. You might, I guess we could think of very large redshift galaxies that the James Webb Space Telescope might see. Remember the balloon? As a balloon inflates, okay, Amanda did this demo for us with the dots. As the balloon inflates, okay, every dot moves away from every other dot, and that's right. ERT remembers that, Ronald. As the dots all move away from us, the ones farthest from us are moving fastest away from us, and that's a model of the universe, right? As you blow up this balloon of the universe, okay, and really accelerate it out there, those dots farthest from you are moving fastest away from you. And that's just what Hubble observed in the late 1920s. And he called it a redshift. And that redshift was a value by which we could estimate the distance of these galaxies. Because if they were farther, they're moving faster. So, see, a lot of this, again, in astronomy, all we have is the light. Spock, we only have the light. So we only can look at the light coming to us. We can't do anything with anything else other than the light. If we could get to these places and set foot on them, well, then we would be able to do more, like we did when we went to the moon. And yes, we went to the moon. Okay. And then when we landed on Eros, okay, the asteroid. So I think that's a pretty good statement of our capability, Keep this in mind. I'm going to show this again. Here's the comparison with Pluto's orbit. Now, we went from the center of that circle where Earth is, okay, in that Pluto's orbit indicator, to Pluto. And it took us 15 years to get there with the New Horizons probe. Took 15 years to get there. So now look at this whole black hole, just across this black hole. And we went in a radio, like it's not a, it was a kind of a sort of a circuitous path. It wasn't a straight path, but still it took 15 years with gravitational assist. Think how many years it would take to get across this black hole. It would take like well over 100 or maybe 200 years to actually cross this black hole. Messier 87 black hole. That's a huge distance. And that's just to the event horizon on the opposite side. This is by far one of the largest black holes that we've ever seen. Of course, that's sort of it would be the biggest black hole we ever saw if we don't include the fact that we haven't seen other black holes yet, right? Yeah. And with Sag A, I mean, we can say, well, it's definitely bigger than that. So,
when you compare those two, Mercury's orbit, what is it, 35 million miles radius?
Yeah.
And when you look at Pluto's orbit, and the diameter, evidently, of the black hole there is several times the size of Pluto's orbit. Yeah. Pluto's orbit is like a couple of billion miles or something.
At least, yeah. And so it takes several hundred years for it to go around the sun, a couple hundred, like 230 or something like that.
Yep. And Mercury takes 88 days.
Yeah, 88 days, So, but you look at this.
Someone asked earlier what the biggest black hole is, as well as what the nearest black hole is. Sag A is the nearest to us, isn't it?
No. Well, we got to be careful.
Or
the answer is it's the largest supermassive black hole to us, but it's not the nearest black hole. There's other black holes that are actually closer to us. And closer meaning closer than 25,670 light years, basically. So I don't know what those other black holes are specifically, but there's nothing within a kill radius of us. Let's put it that way.
Okay.
And I think that's the important thing people need to understand. There's nothing.
Well, yeah, but I think maybe they are hoping like close enough where we could see it from here.
Well,
like with like your telescope, not like.
Well, see, these black holes, though, as I think Daryl was about to say, these are taken in radio light. Okay, our telescopes at Skyter Livestream see visible light, like you see with your eyes. They don't see the light like these telescopes see. This light is way, way, way out past the infrared in the radio spectrum. All right, we don't see the radio spectrum with our eyes, so the telescopes are actually seeing radio imagery. And you can get some pretty accurate radio imagery, but if the object's moving and it takes a long time to get the object, because these are, as I said, very faint. These are very faint objects and take a long time to capture in the telescope, even with our technology. But even so, with such very faint objects, it's problematic to capture them in a way that makes them look sharp. How can we improve that? We can improve it by making a super massive radio telescope. If we can stick a super massive radio telescope up on the moon, say, and so forth, and make it, say, a dish that's 2 miles across, then we can actually observe for much of the time, and would probably be in lunar orbit.
Someone
much
just
of the time.
That.
Huh?
Someone just asked that with the dark side of the moon.
Hey, Daniel. Daniel Twet says, would the dark side of the moon be a great site for a radio telescope? Well, there have been ideas. First of all, the moon is lit on all sides. Okay, it's just the unlit side, right? So when you say, he puts it in quotes because he knows.
Yeah.
Okay.
Or the far side.
Yeah, the far side. The far side. It wouldn't really matter for radio light because those don't have this gigantic field of view. They actually have a field of view that's fairly set. And unless it was made to move and pivot around, like, of course, the VLA, the Very Large Array, that's an extremely delicate system because they move up and down tracks to increase the baselines between the telescopes, and they can close in, they can go farther away for better resolution, and they're the same size dishes, and they can all target the same thing and move. Now, that's the kind of thing we'd put on the moon. And then we'd be able to observe, say, Sagittarius A, and basically instead of a telescope that's 8,000 miles in diameter, we might be able to squeak out a telescope that's about 480,000 miles in diameter. And that would give us much better resolution because that's about the diameter of the moon's orbit, right? So technically, we probably could do it. It's probably feasible. And that would give us far better resolution when we do the same technique that we did with the Event Horizon Telescope, but do it in space.
Per Daniel's question, it has been talked about. I don't know that there are any concrete plans yet. Arthur C. Clarke talked about putting telescopes on the far side of the moon a long time ago, back in like the 1950s or early 60s.
Yeah, it wouldn't really matter. The far side is great because then you don't have Earth to contend with.
Yeah.
In terms
of
its
radio quiet on the far side.
Yeah. And Earth is anything but radio quiet. Right.
There's Earthshine, right?
On the unlit portion on the near side, as it goes through the phases, right? As the moon starts to go around the Earth, more and more of it gets lit up by the sun, but the unlit side is the part that's still facing us as it goes around the Earth. It's just not lit yet because it has to get farther in its orbit, and when it's full, then it's fully lit because the sun's there, the moon's there, so it's fully lit in the face. But as it comes back, if it's coming this way in its orbit, if you're looking early on, well, then only a portion of the moon is lit. And then when it's about a quarter of the way around, then half of the moon appears lit from Earth. And half of it's always lit. Okay, the moon is half lit all the time. You just only see a portion of it depending on our vantage point and its place in its orbit. You got to remember it's a 3D universe. And it's why I could never understand how these flat earthers would say the Earth is flat and look at the moon and say, but that's a sphere. Okay, I don't get it.
Ronald had a question. How can you tell if a black hole is in a certain area without a radio telescope? We see things going on up there. Cygnus X1, I guess, was it the first putative black hole discovered? I forget.
I believe we had gamma ray bursts coming. We also see stars doing this.
We see gamma ray bursts. We see all sorts of wavelengths of light or energy being given off where there may or may not be any star to see there. So it's easy to see them if they have companion stars, like a binary star system.
Or like this.
Yeah, or that they could be feeding off of the companion star. Matter from the binary is falling onto the accretion disk of the black hole, and you're getting all sorts of energetic light or energy being given off from that. Generally how they detect them.
Yeah, and then the other option is knowing you have a possibility, you could do a long-term study like this one, which was, this is like 15-year study or more, and we saw stars orbiting something that wasn't apparently there. And that was basically saying, this is a future target for a more powerful telescope, and that's exactly what we did with the Event Horizon. Now, that's all good stuff. And see, that's what astronomy is all about, is finding all these new things out. And speaking of new things, Daryl, I believe last week we had a lunar eclipse that was pretty interesting. I was part of another stream at that point. Our telescope, that was when we actually had a mechanical failure with the roof, or we would have been streaming it. But that was the one time we couldn't stream it.
Yeah, that was the night I was sick anyway. I did get to see it, though.
Yeah, so did I. I took a picture or two.
Yeah, it was cloudy here, but the clouds started breaking, and I got looks at it from time to time, and the clouds pretty much went away by the end of totality.
Yeah,
and it was pretty cool.
Yeah,
it was a very dark lunar eclipse.
Yes.
There were times I looked, I could really hardly see the thing. It was so dark. And they say that was because of, you might remember when that Tonga volcano blew up earlier this year. it blew millions of tons of dust in the air, and that some of it's still in the atmosphere, and that really darkened the red light being refracted around the edge of Earth, lighting up the moon, the
Right,
so-called blood moon.
And the other thing that you have a problem with, of course, is light pollution in your city. Okay, if you're in a place where you have no light pollution, well, the moon stands out like a sore thumb. But if you're in a place where there's light pollution, you can actually lose the moon in the night sky. The full moon under eclipse is so dark and blood red that you might not even see it. You know, it depends on your light pollution. So I know that there are people that said, I couldn't find the moon. Where you live? Okay. Illinois, where? Chicago. Mm-hmm. Okay, there you go. That's why. You know, there's just no dark sky for them anywhere to look at this.
Well, some people haven't got a clue either. I was coaching some people here. They didn't know where to look when it was. I mean, you know, it rose in the southeast at 8 o'clock here, and it was pretty low in the southeast to the southeast for the entirety of the eclipse.
Yeah. Well, tell you what. Why don't you take us through the lunar eclipse, and let me just remind people of what we saw that one night when we actually streamed the lunar eclipse from here. This was our view from the Sky Tour East that time. We saw this beautiful moon. Here is the red area here of the deeper part of the eclipse. All right. And this was on January 20th of 2019 at 11:41 and 35 seconds. Now, why do I care? Because this little white dot you see right here, that's where a meteor struck the moon during the eclipse. And I've said this ad nauseum, and I'm sorry, but we were one of 5 groups on the planet that actually caught it. So, you know,
that's amazing. I mean, brag about that for the rest of your life. That is amazing.
Absolutely.
Yeah.
Mm-hmm.
I was getting tired of bragging about it, actually.
Don't.
Okay.
It's so cool.
It's amazing. Yeah.
Now, this little guy was about, I think, 18 inches across and maybe a little less, and it made a crater a couple feet across when it hit. And the reason that they see this white dot is because on impact, it hit with such force, moving tens of thousands of miles an hour, that it actually converted all that energy of motion, all right, what we call kinetic energy, right? All that kinetic energy went away, and it ended up creating this light, because what happens is that energy has to get converted to something. So that huge stopping force transmitted all that mass with velocity that made kinetic energy of motion, and turned it into heat. And that heat vaporized this meteor and made a very bright flash for a split second.
Yeah, it was like a pretty good chunk of TNT going on.
Exactly.
You have to wonder how often this happens that we don't even know about, because, like, it's not like that's why you were filming, right? It's not like we were waiting to catch yeah, that's what I mean. You weren't looking for meteors or whatever, like, so I don't know. What are the chances that we
it does happen.
It does.
I've seen lunar observations during a Leonid meteor shower, for instance, other major meteor showers, watching for them to hit the moon.
Yeah, there was
that's clever.
There's a group in Madrid that actually tracks impacts on the moon, and they do see some every year, and they catch the visual, but they also catch it in the infrared too. Wow. And depending on the quality of your infrared telescope that you're using, that's actually the more important data than the visual, because we get this little spot. We saw this beautiful little spot right here at the lower left. Okay, but that little spot is just a white dot. All right, it gives some idea of the impact energy, impact force, etc. But the infrared energy and what happens after the main impact occurs, how it trails off, gives a lot more data, which is also very useful in figuring out the impact or the size and mass and its chemical content, in fact. So there's a lot of really interesting science that can be gleaned from such impacts. But speaking of that, I want to have another kind of impact right now. I would actually like to hear you take us through a deep dive, Daryl, and tell us a little bit more about the lunar eclipse. I know that there's certain times when they occur. There's something called the eclipse season. maybe you can talk about that a little bit, and tell people, what to expect in the season here coming up.
Okay. Well, here we go. All right. On the evening of May the 15th or the morning of May the 16th, if you were far enough east, the moon was full and the moon passed into the Earth's shadow, causing a lunar eclipse. Now, right now, here we are at 7:06 p.m., and you can see the sun is getting over in the west. And I'm going to advance it to an hour. The sun just set, and the moon just rose. Now, this is called an opposition. The moon is 180 degrees from the sun in the sky when it is full. So when the sun sets, the moon rises at full moon. And this is also at the this is early in the partial phase of the eclipse. I'm going to advance it by an hour, and the moon was deep in the partial phase. I can try to zoom in on this some. I don't know how well Stellarium's going to do this, but then by 10 o'clock, and well, let's see. Yeah, this is what I was afraid of. By 10 o'clock, the moon was totally in the Earth's shadow. This is right about midpoint of totality, if I remember right. And one thing I wish I could show you better, but one thing that's happening here, the moon, as it's orbiting the Earth, it passes through Earth's shadow. The moon is actually moving from west to east as it orbits the Earth. The red line is the ecliptic plane. That's the path the sun follows across the sky in the course of a year. It also defines Earth's orbital plane around the sun. But hour by hour, this is going to jump. So I'll back out some. But then by 11 o'clock, the moon had moved to where it has moved out of totality, and we're back into the waning partial phase. And the moon started about here. The moon moves its own diameter west to east in the course of about an hour. So over the course of a couple of hours, it moved a couple of moon diameters from west to east as it passed through the shadow of the planet Earth. This brings up a thing, and it was down to, I guess, waning penumbral by this point at midnight. Somebody at a forum I hang out at said that, well, golly, I know why the moon gets dark. It's because it's in Earth's shadow. And he wasn't talking during the eclipse. He meant every night when the moon wasn't full. He thought that was the Earth's shadow on the moon.
Ooh.
And I remember at a star party many years ago, we had some scouts there. And a Boy Scout, young Boy Scout, early teens, he said the same thing. That when we had a young crescent moon up that night, he said, well, that's the Earth's shadow falling on the moon. And I had to tell him that, no, it wasn't. That was just, the moon was facing mostly away from us. It was a waxy crescent at the time. And everything else we saw was just the so-called, unlit side of the moon. And it was vaguely illuminated by Earthshine.
Daryl, I have to say that indicates someone who doesn't have a good 3D understanding of the solar system right there.
Uh-huh.
Because you could never cast a shadow in that direction knowing where the sun is. It wouldn't work that way. So
this is exactly the case. You can do this with a bare lit light bulb and a ping pong ball yourself. If you have the bare light bulb off in the distance, you hold up a ping pong ball, you can cover the sun, cover the light bulb, and you just made a solar eclipse. You can move the ping pong ball a little bit to the left, and you'll see it a little thin crescent on the right side. And then the dark side is what's facing the Earth. And you can do that by circling the ping pong ball all the way around you, and you can recreate that eclipse.
I did that with a class of kids, like fifth graders. I was in a special lecture, and I went in and I gave everybody, I think it was golf balls. I gave them all golf balls, and we set up a light, and I had them all stand and walk around. It was kind of disastrous because all you heard was clunkety, dunkety, bouncity, bounce. I mean, everybody was dropping the golf balls, but still, you're right. That's a good way to show it.
Yeah. So anyway, this was the eclipse that night. The moon was in eastern Libra, the scales, and here came Scorpius just rising. And over the course of the eclipse, the moon moved this way, closer to the Scorpion. The moon was really, really dark because of all the dust in the atmosphere from the volcano, and it was still very pretty. That's basically what happened on the night of May the 15th. But I wanted to address something else here. Some people say, why don't eclipses happen every month? Well, there's a good reason why. I've talked about this before, and I'm going to change screens here on you now for a minute. Let's see, we'll stop that, and we'll go to the next one. Bear with me just a second here.
And folks, what he's going to talk about is something that shows that the solar system isn't perfect.
Okay, do you see that now? Yep, there it is. Hopefully this shows up well. Bear with me. I'm getting lost here. Okay, it's called orbital nodes or the line of nodes. Now, as I mentioned a minute ago, well, you can see here, this is the Earth orbiting the sun. And that defines that red line in stellarium of so-called the ecliptic plane, okay? And it's called the ecliptic because that's where eclipses happen. Now, the moon is not in the ecliptic plane. The moon's orbit to the Earth is tilted 5 degrees to Earth's orbit around the sun. This isn't the picture I'm looking for. I deleted the wrong one. Sorry.
Well, the blue one you were looking for.
Yeah, the blue, and I don't have it up anymore. Sorry.
Okay. Right.
Hopefully this will get the idea around. Now, there's what's called the line of nodes, is where the Earth's plane, the moon's plane, intersects the Earth's plane. And when there's the line of nodes right there, you see where the moon's orbital plane is tilted 5 degrees to Earth's orbital plane around the sun. But that line where they intersect is called the line of nodes. And when that line of nodes is pointed toward the sun, you've heard me talk about the concept of syzygy before, S-Y-Z-Y-G-Y, syzygy. That's when 3 objects in space make a straight line. Syzygy is when eclipses happen. And if the syzygy occurs at new moon, the moon is closer to the sun than Earth, and the sun casts the moon's shadow on the face of Earth. Now, 2 weeks later, half a lunar cycle, half a month later, at the full moon, again, the moon is on that line of nodes, still pointing at the sun, and that's when eclipses happen. And this is exactly what happened on the night of May the 15th. This is why we don't get solar or lunar eclipses every month. It's only when that 5 degree tilt where the 2 planes intersect is pointing toward the sun. And this generally happens about twice a year. And the solar eclipses and the lunar eclipses tend to happen together. There was a solar eclipse a couple of weeks before the May the 15th lunar eclipse that was down in southern South America, if I remember correctly, is where the solar eclipse was visible. The moon is smaller than the Earth. It's only 1/4 the size, and it's quite a ways away from us, 240,000 miles. So the shadow is converging, and where totality is seen on the Earth is a relatively small part. If you followed the 2017 total solar eclipse, well, you had to be in a pretty narrow path, just, some less than 100 miles wide or something like that, to be in the totality of the shadow. And that was the one I was lucky enough to see from Scottsbluff, Nebraska. But on about early May of this year, people in South America got to see a solar eclipse. 2 weeks later, we all got to see a lunar eclipse because Earth is much bigger than the moon, and its shadow cone is so much bigger that everybody on the dark side of Earth, the backside of Earth, got to see the moon pass through the deeper umbral shadow of Earth, and we saw it turn dark red.
Yeah.
And the other part of this, well, let's see. They tend to happen twice a year. So, like here, it happened in May, and you would expect that line to line up again over here in November. That may or may not be the case this year. I need to look. The other part of this is that line of nodes tends to precess over time. That is, it slowly advances like this, just as Mark mentioned precession earlier. So the months change year by year. This year it was in May. The next one may be November or maybe a little farther in December. And next year it'll probably be in June and December or January. And it'll keep advancing around. And that's why we don't have eclipses every month. Hopefully that made sense.
It does. It does.
Yeah, no. I don't know if you could see it on the screen or not, but people were loving the illustrations and explanations. And I mean, Daryl is just a wealth of information, a walking encyclopedia when it comes to anything space related. So we're very lucky to have him on the show. And yeah, people love you. See, Mark was hinting you have fans. It's true.
Agreed.
We have proof.
Okay.
We know.
And
we know he has fans.
We know.
I guess that's all I have.
Thank you. That was wonderful.
Well, actually, did you want to talk about the spring sky and galaxy season? We'd
okay. Well, we could do that. Tara has questions, I'm sure.
She does, and we're going to get to those.
Okay. 12 minutes left.
Huh?
12 minutes left.
Yes.
Okay. What we have been doing lately, let's see, we'll go to today now. We have been exploring on Sky Tour live stream the spring sky. It's still galaxy season. Whoops. And the sun sets and Orion has gone away pretty much. Here's Betelgeuse. And getting up into the spring sky now, where we have been exploring. I'm going to back out a little bit. This time of year, you've heard me say before that the 1,000 brightest galaxies in the sky, of the 1,000 brightest, 3/4 of them run in a band from Ursa Major down through Canis Venatici. I'll put the animals up here. The hunting dogs, they run from Ursa Major down through Canis Venatici and down through Coma Berenices, Bernice's hair here, and into Virgo and Leo, and on south from there down into Hydra and Crater and Corvus, where we saw the antennae galaxies recently. 3/4 of those 1,000 brightest galaxies are right in this part of the sky right here, and that's where we've been spending our time recently on Sky Tour live stream.
Are there any theories on why that is?
You're maybe getting into cosmology there, but that's. Go ahead, Mark.
I think it really has to do with the distribution of material early on in the universe, and it's not anything other than it is. You know, there's nothing that actually says, okay, this is why the Virgo cluster exists here. Well, we know that the Virgo cluster exists because there's a lot of mass there, a lot of massive galaxies. But how do they all migrate there? When did that happen? Well, we don't really have all those answers.
Like, are there more stellar galaxy, the nurseries? The what is it called? I had it a second ago.
We talk about the H2 nebulae, the H2 regions.
No, it's like where stars are born.
Yeah,
aren't they like stellar nurseries?
Stellar nurseries.
Yeah. Are there? Is it a greater population in that area for stellar nurseries as well? Are more stars being born there than anywhere else? Or
with more galaxies, you're going to get more stellar births because those occur in galaxies.
Is there any correlation between them being the same place?
It depends on the scale you're looking at. I mean, we're in the local group, and the biggest concentration of matter in our part of the universe, not the galaxy, but the universe, is right about here, where Coma Berenices and Virgo and Leo all come together, is where the Virgo cluster is. And we're following that direction in space. Everything else around us is moving that direction in space. And from the Virgo cluster of galaxies, everything is moving on down farther to the southeast, if I remember correctly, toward the Great Attractor, which is below the southern horizon here, but it's in Triangulum Australia, I believe it's called, Southern Triangle, that even the Virgo cluster and pulling us along with it is headed down this direction toward the Great Attractor.
And keep in mind, too, when he's telling you this, keep in mind that the local group of galaxies like us, Messier 33, the Triangulum Galaxy, which I showed you earlier, which was this galaxy, and Andromeda Galaxy, which is physically near it in space. The Andromeda Galaxy is actually heading toward us, and in a couple billion years, it'll pass through us, and we will either be absorbed, ripped apart, whatever, by this big giant monster. And it is a monster. It has 1 trillion stars at least. We have about 150 to 200 billion. So we're going to get either absorbed, and maybe we have a future of being turned into a whole new type of galaxy, or something we've seen out there that we don't understand yet how it happened, and maybe we're in the middle of it.
Yeah, see, I have a gazillion questions like that. Like, does this kind of thing happen more often in this area, like where galaxies are going through each other and stuff? Does that help populate? Like, why this area is so much more populated than other areas? Like, are there? Well, I mean, we're talking about galaxies, so it's not like there's less black holes in that area, because
this is where you're getting from galaxies to clusters of galaxies to superclusters, and then you're in the realm of cosmology, where we're part of the oh golly, I forget what's the name of the local supercluster is we're part of, and this is where the universe starts looking like a spider web.
Talking about Laniakea?
Laniakea, thank you.
Now, I know that I think, Tara, before we started up, did you have questions about galaxies? Did you have a question or so? I wanted to make sure, because I wanted to give you a chance here to ask us a question about that.
No, nothing specific. I'm sure I have questions, but I was thinking more about gravity and light, I think. But
can I show one thing real quick?
Yeah, go ahead. Okay. Then we'll go over to Tara.
This is just mythology. Okay. If you've never heard the story about Orion the Hunter and the Scorpion in mythology, okay, you never see Orion and the Scorpion in the sky at the same time. In mythology, the Scorpion stung Orion and killed him. And the gods put them both in the sky, but they separated them so they would never fight again. As you see here, Orion is mostly gone. Betelgeuse is just barely up, and he's about to set. And I want you to watch what happens to Betelgeuse here over the course of a few minutes. Okay, there goes Betelgeuse. And here comes Antares, the heart of the Scorpion. So Betelgeuse sets, Antares rises. And say bye to Orion and hello to the Scorpion. Antares is the heart of the Scorpion. And incidentally, Betelgeuse and Antares are the two best supernova candidates that we know of in our part of space. And there went Betelgeuse, and here comes Antares right there this time of year. Thank you. I just had to share it. I just had to throw that in there.
Actually, that's a very good point, because you have one red star setting, one red star rising, basically.
Yep, both red supergiants.
Yeah, but keep in mind that Betelgeuse used to be an O-type star, bright blue.
Yeah.
And it migrated to that over a period of maybe about 10,000 years. So literally a few million years ago, Betelgeuse was a bright blue star in the upper left of Orion. All right.
Where would you like to go here, Mark?
Well, I think that I want to have Tara ask some of her questions, because she had some really cool questions to ask.
Okay.
So we'll just say thank you, Daryl. That was wonderful.
Very good.
And we'll be prepared for looking at the galaxies next week.
All right, then.
Thank you very much, Daryl.
There you go.
There's our Tara down there.
Well, I know we don't have much time, but I do have one question about gravity. So from what I understand, gravitational waves go away from the object that's emitting them. So what is the process or mechanism that causes these waves to pull things or push things in that opposite direction or towards the object that's emitting them? How does that work?
That's a really good question. And the thing is, we all know that gravity works because we can drop something and it'll fall, right? So you say, well, wait, what's causing it to fall, right? You can get very philosophical about gravity, or you can actually get very discreet about it and say, I know we sort of have an idea what's going on. Gravitational waves aren't noticeable as ripples unless we have two very massive objects that collide, merge, or otherwise do something that causes a massive gravitational wave surge. Colliding neutron stars can cause a gravitational wave, a ripple. Black holes merging can cause gravitational waves rippling. And those ripples are actual ripples like ripples in water, but they're actually ripples of gravity that are detected. That's the easiest way to describe these. Now, gravity moves out and away from the object that's radiating it in this regard. So when the detectors on the planet, LIGO detectors, the Laser Interferometric Gravitational Wave Observatories, say that 3 times fast, when the LIGO detectors detect these gravitational waves, just like with the Event Horizon Telescope, the detectors are not in the same place. You've got one on one side of the world, one on the other side of the world, and the gravitational waves, the ripple coming from a merger of neutron stars or black holes, hits one detector, but then hits the other detector after that. And that difference in time is very helpful in trying to pinpoint where it came from. It's 2 points of observation are required to get a vector to where it's happening, right? So we're getting that ripple, but those are like above and beyond the normal gravitational forces that we feel. Those are actual, think of it as overpressure, high-end gravitational waves, very powerful waves like in the ocean. The ocean has waves rippling on it all the time, right? Think of that as the normal gravity, but then all of a sudden you get a big crashing wave. Well, that's sort of like a gravitational wave. It's propagating in the same way. I see you have mystery on your face.
I do have mystery, but I think we're out of time. But that's really cool. It's just fascinating. So thank you.
Well, I appreciate
I wanted to see you drop the black hole on Tara again.
Oh, you like that?
Do it. Oh, she got absorbed. Sorry, I couldn't resist.
That was really good, Amanda.
I didn't even go to a noodle.
Good timing.
Yeah, she came back.
She got stretched into an infinitely long string of spaghetti. You know, Daryl, thank you for that deep dive. Thank you for talking about the eclipses. That was wonderful, man. I really appreciate it. Amanda, thank you so much for being here with us. You, as always, make it a delight. And Tara,
this
you're
is a
a
great show
lifesaver.
as always. We learn so much and have good laughs and in awe of amazing pictures. I mean, and it's free.
Yeah,
like you can't lose. Great way to spend
No.
a Sunday evening.
No, you're right.
I agree.
Well, I'm gonna go check out the observatory here, folks. If you guys want to join us, I'm gonna go see what the weather looks like out there, and I will put up a stream for you to come check out as
Sky
soon
Tour
as
live stream with Mark
Sky Tour
D'Antonio
live
on
stream.
YouTube. Check it out.
Yeah, and Daryl is there with us as a co-host, and I think you're up for that tonight. If we go, are you?
Yeah, I'm going to go fix some dinner first. But
yeah, of course. Yeah, we're not ready to go for. The observatory power doesn't come on for another hour. But anyway, guys, thank you for blowing another 2 hours with us. We really appreciate it. Had a great time with you, and remember, black holes are really crazy.
Yes, they are.
We'll see you later, guys.
Good night, all.
Bye.
Good night, everybody.
Take care.